Okay, so let's get into it. We're doing a deep dive today on a really core infrastructure challenge. How do you take decades of old school coaxial wiring, with all the cable TV channels and
It's
data,
legacy RF
right,
signal.
all that RF, and move it onto a modern fiber optic network without having to just rip everything out?
Mm-hmm.
Well, the specific piece of hardware we're looking at is this Thor broadcast transmitter, the FRF-1550-TX-8mW. And its whole job is to take that entire electrical spectrum, that whole 45 to 870 millihertz lineup, and just turn it into light. Okay, so looking at the core function, one thing really jumps out, the wavelength. It's specifically 1550 nanometers.
Yeah, that's very deliberate.
I mean, why that one? Couldn't they use something more common, like 1310? Isn't that a standard for a lot of data traffic?
It is, yeah. They absolutely could have.
Yeah.
But 1550, that puts you right in the C-band.
Okay, and the C-band means what exactly?
It means it's compatible with EDFA.
Erbium-doped fiber amplifiers.
Exactly. So the real secret sauce here is that you can optically amplify that signal to, really high power levels. And that's what unlocks what they call fan-type distribution.
So point to multipoint.
Right. You can broadcast that entire signal stack to tons of different locations without ever converting it back to an electrical signal. It just makes the network massively scalable.
That simplifies things hugely for, say, a campus or a large building. But what about for the technicians on the ground, the people actually maintaining this?
Well, for them, it really comes down to automation. The unit has automatic gain control, AGC,
Right.
which is it's essential. It just constantly monitors and manages the RF level coming in. It keeps it in that perfect window between 11 and 29 dBmV.
So no one needs to go out and manually tweak a dial if the input signal fluctuates a bit.
Exactly. You get a consistent, stable optical output no matter what.
And the quality specs in the source material seem to back that up. They mention using a highly linear DFB laser. For you, the listener, what do these impressive numbers like a CNR better than 50 dB and CTB less than a nega 63 dB, what does that actually translate to?
It translates to a perfect picture, full stop. That linear distributed feedback laser is what keeps that huge 800 plus megahertz band of channels from, interfering with each other. When you see numbers like that, it's basically a guarantee that even over 10 kilometers of fiber, you'll have zero visible noise, no artifacting, just a clean, stable, high-definition signal for whoever's at the other end.
And this is where the flexibility comes in with the real-world applications.
Yeah.
You can use it for a simple point-to-point link, or you can get complex.
Yeah, you can integrate it with PLC couplers, with fiber splitters, and do these huge multi-site deployments.
And critically, it outputs the industry standard RFOG signal, RF over glass.
Yes, which is key. But, there was another application mentioned in the source that I found really fascinating.
Oh, the security feature.
The security feature, yeah. The ability to create high-security fiber breaks.
So what exactly is that?
It's about network control. It means you can use this to completely eliminate the coax signal return path from a specific location.
So no data can get back upstream from that point.
Precisely. It's a massive security enhancement. You're effectively stopping any signal ingress or any, unauthorized upstream transmission.
Wait, okay, so if signal integrity and security are that important, we have to talk about what the source calls the most critical installation requirement. It sounds like the biggest single point of failure.
Oh, absolutely. This is non-negotiable.
They stress that you must use an SKPC connector, the angle polished connector. Why is that specific part so vital?
It all goes back to the power and precision we were talking about to get those clean signals. If you take a legacy fiber cable that's terminated with a standard flat connector, a PC type,
Which a lot of older installations might have.
right, and you plug that in, you create back reflections, light literally bounces back down the fiber and into the laser.
And that just, it destabilizes it.
It collapses the entire system.
Yeah.
Instantly. All those high-performance metrics we just discussed, they're gone. The signal becomes completely unusable.
Wow. So you have to use a specific optical jumper to convert from that flat type to the angled one.
You have to. It is the difference between a pristine signal and, well, nothing at all.
So let's pull all this together. This TAA-compliant hardware, listing for just under $4,000 for the 8mW model. It's much more than just a simple converter, isn't it?
It's an enabling technology. It's what allows you to bridge these two different eras.
You're swapping out the old constraints of coaxial cable for the massive capacity and stability of a modern fiber network.
Exactly. And when you think about it, that contrast is what's really telling here. You start with this kind of chunky, relatively imprecise Type-hit connector from the old coax standard.
Right, the screw-on plug.
Yeah. And the signal that comes out the other end demands this incredibly precise, angle-polished SEPC connector just to operate flawlessly at the speed of light.
It's a huge leap in precision.
It is. And it leaves you with an important question to think about. As our demand for capacity continues to soar, how much longer can these older physical connection standards really remain compatible with the precision required by light-speed delivery?